B naught value is just going to be equal to K omega Z hat cross B naught. So what does that say? Now, they're really vectors because they're taken into account here. I didn't write them as such. It's a complex magnitude of it. But basically what it's saying is that you take the direction of motion, you cross it with the direction of the electric field, you're going to get the magnetic field. Well, if the electric field and the direction of motion are crossed, the electric field is going this way, what must the direction of the magnetic field be? It's got to be perpendicular to E and perpendicular to Z. It's the only way that can happen. Let me do this in red. It's going to have to be like this. So that's little, that one's little. That one's going that way, that one's going that way. And they're perpendicular to each other every time. Interesting. Because there's an omega relationship here. As one gets bigger than when the other one gets bigger. Now you don't know by how much because this right here kind of relates the magnitude. That's going to modify that magnitude. That's a multiplier. And actually, I'll tell you, the electric field is much, much bigger, like 10 to the 6th, if I'm not mistaken, times bigger, without looking in the book, in terms of magnitude than the B field. Interesting. So just applying, again, these cross products, applying Maxwell's equations, you get all this. So that really tells us, follow along so I say it like the book, so when we're reading over this. Or you can rewrite this, that just the amplitude of the B field is equal to 1 over C E naught. And I was off by 10 to the 6th. That's 10 to the 8th. 10 to the 8th. So that's 10 to the 8th. 1 over that's 10 to the negative 8th. What does that mean? So E naught is about 10 to the 8th times bigger than B naught. So when we think of electric field, a lot of times, with an electromagnetic wave, I apologize, I got ahead of myself. When we think of an electromagnetic wave, we most of the time think of its electric field component only. We don't think about its magnetic field. It's 10 to the 8th. It's 100 million times smaller. 100 million times smaller in magnitude. So any effect there, it's going to be that's what we're going to magnetic field. It's going to be really, 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 really strong field. And that's why I was in the class I was saying if an electromagnetic wave has electric field and magnetic fields, well, if you mess around with the electric field of it, it's called the electro-optic effect, you can mess with the wave a little bit. You try to mess around with the magnetic field, since it's so much smaller, you're going to need 10 to the 8th times bigger in magnitude field values. 100 million times stronger field. Or you can think of it as with the same field, it's 100, the effect on that light wave with the same level of field is 100 million times less of an effect. Much, much smaller effect that you notice on it. Okay. Now, you can write this. Normally you don't see this in terms of Z. In general, the way they write this as the electric field, they put it in terms of R. And this is that complex magnitude there. And that's just equal to E naught. That's that complex magnitude. E to the I K R minus omega T. And that's in the n hat direction. And then it'll say B of R and T. And we're writing this with the complex there. Let me write this as just a vector. Better way of saying it. As call it a couple different ways. 1 over C E naught minus, and this is just from right here, putting this in there, E naught I K R minus omega T, and taking this times K hat cross N hat, where K hat's the direction of the wave, and N hat, K hat's like Z, it's how the direction the wave is going, and N hat is just that direction normal to it. Or you could just write this as 1 over C K hat, which is the direction of the wave, cross it with the electric field. They call N the polarization vector. Still got little bugs. I thought I killed them all. The temperature killed them all. Polarization vector. Now, because these are crosses with each other, what would be the direction of the polarization dotted with the wave number vector? Remember, the wave numbers basically tells us the direction that wave is going. And that's a unit vector of that wave number. N hat is it's the plane of polarization that it's oscillating in. What's that going to be? Somebody tell me. You can't, because I'm in the barn and you're, who knows, you're forward in time. 0. Because they don't have anything in the same direction. They're completely perpendicular to each other. The wave is going this way, but they're either oscillating in this plane or in that plane, in the y direction, in the x direction or the y direction, as they move in Z. Which one's an X or Y? Well, it just doesn't matter. It's how it was set up. It's the direction of your antenna that you had initially in your electric field. And that's the way they travel. Monochromatic plane waves. Figure 9-10 is a really good picture to put in your head. If you really want to get a visual of it. Maybe even put it in your notes. When I have to see things. When I see electromagnetic waves, electric field and magnetic field moving, that's a kind of a classic picture that people use that you can see in your head. Think of it as like this. So the electric field goes up, the magnetic field's going to go out this way. So as it travels, they're going out. Can't do that real good. Let's try it again. They go out. One goes down, then they go back up, and one goes down. They travel in concert. When one gets big, the other one gets big. They're in phase, you could say. Of course, their magnitudes, B isn't going out as much as E. It's only going out 100 million times as far, 100 million times smaller. So I can't really do that in my hand real good, right? I'm not that precise. But just for demonstration purposes, they're doing this as they're moving with time. Okay? That's how, and honestly, if you're 1860s, 1870s, you're like, wow. Maxwell basically, and he was a young guy when he figured this out, 20s and 30s, if I'm not mistaken. Wow. That's the way these waves work. And all based on understanding, once you know these fields of the Laplacian, which is del squared, one of these E fields, the del operator times one of these E fields, the dot product of these E fields, how much they change in the direction that they're going or in a certain, and how much they change perpendicular to that direction, which is the curl. So all those things tell us how much the rate of change and going forward that it's going. That's del dot. Del cross is what's its rate of change perpendicular to the direction it's going, in a perpendicular direction. How much does it curl back on itself? Just by knowing the mathematics of that and from these fields, We can get a relationship of it. And from those two, it's just, they're doing the math. Makes you wonder if Maxwell hadn't figured all this out, how long it would have took to get there. There's a lot of things in science you sometimes wonder about like that. And yeah. Makes you also wonder if the converse is true. Was there somebody killed by the plague or something or got ran over by a horse in the 1800s, or killed in one of the Napoleonic Wars, or just got hit upside the head by some guy in a bar fight? What could have been? And but we live with what we got, right? All right. Thought you might find that interesting. That's monochromatic plane waves and Maxwell equations.